Hello, my name is Allison Rice, and today I hope to convey my strong commitment to teaching and utilizing innovative and evidence-based teaching methods in the classroom. My goal is to create a positive learning environment which is inclusive for all students. This involves the use of not only traditional lectures, but innovative activities such as a flipped classroom format and science demonstrations, as well as the use of technology in the classroom, such as clickers, enabling students to gauge comprehension in real time. During my time at USC, I have been able to work with both small classrooms with up to 300 students, and also have been able to show ways to disseminate concepts outside the classroom to the broader community. Today, I will give a teaching demonstration on the Vesper theory for a smaller classroom setting. Good afternoon, class. Okay, so today in class, we will be talking about the mystery behind the acronym of the Vesper theory. So everyone calls it the Vesper theory, but what does it really mean? And although the acronym doesn't really match how we say it, we're going to figure out all the details behind this concept today. Who in here likes Ed Sheeran? I know I do. So Ed Sheeran sings about being in love with the shape of you, but what about being in love with the molecular shape of you? This is what we're going to learn today. So the first thing we have to know is what is behind this acronym. So it's actually VSEPR, which stands for Valence Shell Electron Pair Repulsion Model, which predicts the shape around a central atom. So a molecule has a shape that minimizes the electrostatic repulsions between valence shell electron pairs. And this is when the minimum repulsion results when the electron pairs are as far away as possible. So saying all these words sounds super confusing, and you're probably like, why is she telling us all this? But you'll find out in the preceding slides about why I'm saying all these things. So the first concept, though, to learn is about steric number. So understanding steric number is the most key fact in learning and getting these questions right about Vesper theory on an exam. So steric number is the number of lone pairs on a central atom plus the number of atoms bonded to the central atom. So the steric number is determined from the Lewis structure, which you guys all remember from previous lessons, which you better remember from previous lessons is what I should have said. So steric number determines the bonded atom lone pair arrangement, which can be abbreviated as BALPA, so you can remember it better. So this is the shape that maximizes the distance between the valence shell electron pairs. So let's do some practice about steric number before we move on to the next concept. So say we had an example with a generic element we'll label as X. So say we had this around the X. What would the steric number be? Yes, you're right. So someone said 4 in the class. So the steric number around the central atom is 4. Great job. So what about a little more difficult example? If we had this example, what would the steric number be? Okay, so I hear someone said 8. I also hear someone say 4, and I heard someone say 6 as well. So we remember that lone pairs count as one entity. So we know that it's 1, 2, 3, 4, 5, 6. So the steric number is 6 for this example as well. So good job, class. So always remember, go back to the basics of the steric number when we get into the harder examples. So moving on, we have to think about the geometric arrangements in terms of Vesper theory. So when the steric number is 2, it has a shape called linear that is 180 degrees away from the central atom. This brings me to the mystery of what is in this garbage bag. So do you guys think that I just brought in garbage today? No one. Okay. So today, we will use balloons to help us understand the Vesper theory. So starting with, we have 2 balloons tied together, and this is representative of the linear geometry, where the 2 atoms are 180 degrees away from the central atom. Sometimes it's easier for me to remember things if I take a concept and connect it to everyday life, such as using the balloons. But it's also a good idea to visualize these molecular models using a molecular model set that they sell in the student bookstore. So in this case, you can see that for a steric number of 2, the angle is 180 from the central atom. So what about when you have a steric number of 3? Then we add a third balloon to our 2 balloons, and it becomes the trigonal planar shape, in which there's 1, 2, 3 atoms bonded to the central atom, and in this case the angles are 120 degrees in all cases. The steric number is 4. It's called a tetrahedral, as shown in the methane example, in which the angles are 109.5 degrees away from each other. Okay, what about the trickier ones with steric numbers of 5 or 6? So, if you have a steric number of 5, it's called a trigonal bipyramidal. We see that we have 120 degrees in this case here, on this plane, but we also have 90 degree angles in this way. So this one is especially important to visualize. So lastly, the steric number of 6, called an octahedral, in which all atoms are 90 degrees away from each other. And I think the most difficult part of this whole part of the lesson was me putting all 6 balloons in my hand. So remember this when you have questions on the test about this. All right, class, who is ready to help me with an example from today's lecture using the smartboard? Okay, Maria, how about you? So the first thing you want to do is to start off with drawing the Lewis structure. And then you're going to want to tell me what the steric number of this molecule is.
Okay, so I think that the steric number is going to be 6 because we have 6 atoms.
Okay, Maria, I see the reason why you think this, but it's important to remember that the steric number is based upon how many atoms are around the central atom. So we know the central atom is phosphorus, and we have 1, 2, 3, 4, 5 chlorines around the central atom. So since there's 5 bonded chlorines around the central atom, what is the steric number?
It would be 5.
Yes. So then what is the bond atom lone pair arrangement then for this molecule?
It would be trigonal bipyramidal.
Wonderful. So I'll go in a little bit more detail about the steric number through more examples. So we know when we have a steric number of 2 for this beryllium chloride structure, we have beryllium and then 2 chlorides on each side. So this brings me to the question though, if the class was looking at this and you saw beryllium and 2 chlorides attached to it, would you say that the steric number was 1, 2, 3, 4? So some people might, but you guys have to remember steric number is based on the central atom. This is a crucial fact. So steric number is based on central atom. And it has a linear geometry in which these 2 atoms are as far apart as possible from each other. This brings me to the more challenging example of a linear geometry, dealing with the Lewis structure of hydrogen cyanide. So let's draw that on the board and then discuss it in a little bit more details because it's kind of tricky. So I really also want to point out that you guys need to remember the Lewis structures from previous classes because they don't go away in Gen Chem. Okay, so we know that the central atom is carbon. So that's important. That's the first important step. So what is the steric number around the central atom? Do we want to say that the steric number equals 2, or do we want to say that the steric number equals 4 in this case? Oftentimes people count the triple bond as 1, 2, 3 instead of counting it as a triple bond. So in reality, the steric number is 2 for this example. Okay, so that brings me to an example of the steric number of 3 with boron trifluoride. And the central atom of boron has a steric number of 3 with 3 different fluorines bonded around the boron. And this has the bonded atom lone pair arrangement of trigonal planar. So another example of a steric number of 4 is methane. So we have a central carbon atom and 4 hydrogens bonded around it, so that gives it a tetrahedral geometry. This brings me to the steric number of 5. So in this example here with the central atom of phosphorus, there are 5 fluorine atoms surrounded to the central phosphorus atom, forming a trigonal bipyramidal. And then lastly, what about the steric number of 6? In this case, there's a central sulfur atom surrounded by 1, 2, 3, 4, 5, 6 fluorine atoms to give the arrangement of octahedral.